math, right? 20 divided by 3 is 7, yeah, okay. I can do this, I can show this without this transformation. This transformation puts it, maps it to the standard normal or the t distribution with a mean of 0 and a, yeah. We can draw the picture. Oh, sorry. Wait. So this p-value is much, much less than our alpha equals whatever significance level that is specified a priori.
What does the specification of the alpha? It's arbitrary?
No, I mean that's so. I think the question is, where does the specification of alpha come from? So that's a important question. I mean, that is. So within the realm of statistics, it is largely arbitrary, but conventionally people like this as the probability of being wrong as a cutoff, but fundamentally it is a matter outside of statistics, and it is a matter of what is the cost of being wrong. Okay. If you can say, I'm wrong with only a 5% chance. But if being wrong, if the decision to reject the null hypothesis in your decision-making framework, and you follow this and you reject the null hypothesis, and that is a decision, and actions result, and those actions could kill people if you are wrong, you don't want to have a 5% chance of killing people. Oh. Mm-hmm.
Let's say that alpha is 0.01.
Mm-hmm.
How is that described in that graph? Can it be?
Let's see. First, let me draw 0.05, and I'll draw both alpha A and alpha B. Okay. In this picture, alpha of 0.05 is here. I mean, sort of, right? Okay. This is what we call the critical value. That's a T. You can use a Z, same thing. And from here, this part here, this area of the probability here is 0.025 or 2.5%, and over here, from here on out, it's 2.5%, and this is half of alpha. And if this is where, so this is what we have specified for alpha, that specification maps to this picture, and says if we get a test statistic that is further out than our critical point, we will reject the null hypothesis. Okay, so if the null hypothesis is true, we will have sample mean, this transformed value, but our samples will come in according to this distribution. If we're only going to sample one time in an experiment, but if you simulated thousands of samples, if the null hypothesis is true, they come according to this distribution. And this is the thing that we can do math and transform and we can get here. And we will have some of those samples that are somewhat unlikely. You know, if we did this 1,000 times, we're going to get, you know, a few samples that are up here or down here that are very different from the bulk. Those are the extreme samples. They're unlikely, but they will naturally occur with random sampling, with just the probabilities come in. And so alpha comes in, we have our alpha. We put the alpha probability at the extreme ends of the distribution, and we call the cutoff point the critical value. And if we have a statistic that comes in anywhere in the extreme end of this, from this critical point, we reject. We reject the null hypothesis, which means our decision is that this is wrong. We decide, we reject the null hypothesis. We reject this distribution. It's not right. This will happen. Now, in this picture, if this is correct, we will get these things up here. And we will reject the null hypothesis alpha % of the time. And we are wrong when we do that. So this can be correct. And we decide that it's wrong. We reject it. Even though it's correct, we erroneously, incorrectly reject 5% of the time. I'll draw a little chart thing that'll...
So it would be better to have a lower alpha.
That's correct. You are more certain if you have a lower alpha. This is why people publish the p-value, and knowing alpha is on the side. People do not publish a result saying we reject at alpha level 0.05, because here we would reject the null hypothesis at alpha of 0.05, but much stronger is to say at this level, and even much, 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 much stronger So this is the, so it is used, this is a degree of extreme.
What are common p-values?
So it depends a lot on the field. Let's see. The standard, the science, social and physical sciences, often you see a p-value on a study of 1.8%, and they're happy with this p-value, and they put an asterisk by it because it is less than 0.05. And they, if it's a medical study, there's a whole bunch of things that they're measuring, this level and that whatever changes and everything. So you have many things. And you have another one that's, this is your, whatever. Another p-value for a different assessment is, 7.2%. It doesn't get a star. I'm serious with the stars. Because it does not represent stronger than alpha level evidence, statistical evidence to reject, to make a decision of rejecting. And, then there's the, this thing, some extreme number, but there is p-values in publications tend to be this kind of thing, because if it was this, you already know it. This is so strong that such overwhelmingly strong evidence against the null hypothesis. This strongly rejects the null hypothesis, so strongly that unless you have been under a rock your whole life, you goddamn well ought to already know it. Not always. It might be new research. No one knows that this is, but generally speaking, people are working, research work is working on the boundary.
To get p-values with star, do you need to analyze more data? Not necessary, or yes, necessary?
Yes. That's right. I mean, fundamentally, that's right. So we talked about alpha, which is the significance level. The p-value, you can kind of forget some about that and just look at the p-value. Is it small or large? When I was doing government economics forecasting, revenue forecasting for the government revenues for the legislature, had a 2-year forecast of money they were allowed to spend. And we did the forecasting to tell them, here's what you can spend. And we did analysis with how accurate do we think our forecast is. And they're terrible. So if we tried to get something significant at this level, forget it. We would often be using 0.2 or 20%. Yeah, and it's the only thing we could do, because if I tried to make, this is analogous to a confidence interval of 80% confidence, or of 95% confidence, or of 99% confidence. If we tried to be anything better than 80% confidence, we were saying, the universe, we have no idea. If we want to be really confident about the number, the range is so huge. I mean, so it can depend. Yeah. But there is, sorry, it's distracted. When we'll take a break, maybe, and then we'll come back and talk about the power of a test, of a statistical test, and that you can't have the best of both worlds unless you have a lot of money. So money buys you large samples, or lots of analysis, or whatever. But you need money if you want to overcome the mathematics balance between the significance level that you might achieve and the power of the test. They're in balance. And your observation of analyzing a lot of samples, that is exactly the only thing that can overcome that limit. So that's how you get things done. Are we? Let us, let's see, it is 5:30. Let's take a 15-minute break, and we